So this time around, we're going to take a look at dihybrid crosses. The difference between a dihybrid cross versus the monohybrid cross we did in the last pencast is that we're going to look at two traits at one time instead of one. So we'll use our ever favorite mice, and in this case, we're going to take a look at two traits. One trait will be for fur color, and the other trait is going to be for their ability to run. In the case of fur color, we have a dominant allele, which we'll designate with a big B, and that's going to code for black fur. We have a recessive allele, which will code for brown fur. For the running ability, we have a capital R, which will code for their ability to run in a straight line, or we'll just call it flat out running. The recessive allele is going to code for their inability to run in a straight line, otherwise known as waltzing. So for this particular cross, I think what we'll do is we will first take a look at what happens if we cross a heterozygous black homozygous running mouse with a brown waltzing mouse. Now, the biggest part to this is to figure out and determine how the gametes that each parent can contribute. So what makes this one a little different from the monohybrid is that in each gamete, we have to make sure that we have one half of each chromosome pair represented. So in this case, the B's are representative of a gene on one chromosome, the R's are on another. So if the first parent goes through meiosis, we can find that we could end up with gametes where we have a combination of a big B with a big R. Now, this same big B could end up combining with the other big R. But you'll note these two gametes are exactly the same. So when we go to determine what we're going to use for the Punnett square, we're going to actually just ignore that. Now the little b could also match up with the big R. And you could get that for a gamete. You could have the little b matching up with the other big R, in which case, once again, we're dealing with two that are identical, so we're going to ignore the one that's the same, and we're only going to deal with gametes that are different. Now, for the other parent, that is a brown waltzing mouse. If you notice, in terms of both alleles are the same, so no matter what chromosome ends up with which at the end of meiosis, little b, little r, little b, little r, little b, little r, no matter what, that parent is giving a little b and a little r. So that's the only thing we're going to write down. When you're doing a dihybrid cross, you want to make sure that the only gametes you are doing are the ones that are different, because otherwise you could run into a problem of completely, well, maybe not completely, but you're going to end up maybe making a silly mistake. Alright, so once we have the gametes created, which if you remember in the monohybrid one, that one was your step 3. We have step 2 is figuring out the parents. Step 1 up here, where we figured out the alleles we were going to use. Step 4, you're going to build your Punnett square based off of the gametes. So I'm going to do that one over here. And just like monohybrids, you're going to take one parent and place them across the top. So I've got a big B and a big R, and I have a little b and a little r. One gamete, the other gamete. I'm going to take the gamete from the other parent and put that down the side, and I'll do a little b, little r. From that, we construct the Punnett square. Now, when you finish or complete the Punnett square, I should say, as in step 5, you're going to look at what gamete, if it matches up with one from the other parent, what kind of kiddo could you get? So in this case, with the first one, if I bring that one down and this one over, big B, little r, big R, little r. If this one matches up with this one, little b, little b, little r, little r. So now I can take a look at determining the genotype and the phenotype ratio outcomes. For this one, my genotype ratio will end up being 50% big B, little b, big R, little r, to 50% little b, little b, little r, little r. My phenotype ratio will end up being 50% black running. Now, dihybrids, really important. The two traits together equals the phenotype. You don't separate them out. Okay? To 50% brown waltzing mice. Okay. So that one not too bad. Each parent didn't, could only contribute very few gametes. So what happens though if both parents are heterozygous for both traits? So let's take a look at that one. So let's say we have two black running mice, but they're both heterozygous for those traits. Okay. How many gametes can each parent contribute? So we'll take a look. So if this chromosome ends up with that chromosome at the end of meiosis, I get a big B and a big R. If this chromosome ends up with that one at the end of meiosis, I have a big B and a little r. Those two are different. If the little b ends up with the big R, there's another one, and the little b, little r. So this parent here can contribute 4 different gametes. Since the other parent is also heterozygous, we know that that's going to be the exact same type of gametes. Okay. So now I have to create my Punnett square using all 4 different gametes. So I take one parent and I put one parent across the top. Okay, and I pick the other one and I put it down the side. And now we have to fill out what ends up being the most complicated Punnett square for a dihybrid that you guys will end up doing in class. And really the most complicated dihybrid Punnett square you'll ever do. It's just in the interpretation that can be tricky. So if you give me a second, let's fill this in. Alright, there we go. So now we have to go through the process of interpreting. If you go through and count up all the different genotypes you actually end up with 9 different genotypes. Generally on dihybrid crosses, we're going to end up asking you about phenotype ratios, so let's take a look at what we have. I'm going to start with this one. This, in the very first upper left corner square, we have, for both traits, the dominant allele is being expressed. So we have a black runner. Well, let's find out how many black runners we have. So we've got 1 there, 2, 3, 4, 5, 6, 7, 8, 9. So you end up with a grand total of 9 black running out of the 16. If we find another one that's different, how about black waltzers? So we know we have at least one of those, so we can write those down. A black waltzer. That's where you have on the first allele the dominant traits express. The second one we have to have 2 recessives. So I've got 1 right here. Okay, big B, little r. There we go. And a big B, little r. We end up with 3 of those. Okay. Now if I look, what about if the first one got brown, but a runner? So a brown runner. Okay, for my brown runner, I need 2 little b's followed by a big R something. So 2 little b's, big R something. 2 little b's, big R something. We have 3 of those. And then we are finally left with the last one, which is a brown alter, where both are recessive and you only have 1 of those. This phenotype ratio here is a very typical ratio when you're dealing with 2 parents that are heterozygous for both traits. This will be the phenotype ratio where you end up with 9 dominant traits to 3 dominant recessive traits to 3 recessive dominant to 1 recessive. So that's how you end up doing a dihybrid cross. There are tons of examples out there on the internet. If you want to go out and check, you can get tons of practice problems, but the best way to get really good at these is to continue to practice. So have fun, and don't forget to talk to your teachers if you have any questions. See you guys later.